One important property of dealing with all types of waves is one known as interference. And this property is best explained when you have multiple waves present. And it's the main thing that distinguishes classical waves from particles. And that main property can be summarized very, very quickly. When you have multiple waves and they're allowed to interact or interfere with one another, they simply add together as vectors. Now, this adding together as vectors may not sound, like anything different than you would normally deal with. However, it becomes much more different than what you would expect from, say, particle behavior. So here we have a screen for a traveling wave. So I can draw one traveling wave like this in blue here. And let's say I were to overlap it or place another wave at the exact same time sequence and have it go so that it is out of phase with the first wave and opposite in its amplitude. So this is the best I can do. Let's assume that all of these little peaks and valleys are roughly the same for the red and the blue things. They're just shifted a little bit. If you were to add these two things together and look at the total, and if you recall from forces, the total is what you see. What you will actually see when you add them all together is nothing, right? Because one of them is positive at a particular point in time, the other is negative. So when you add a positive and negative vector together, you do get 0. So what that means is you'll see nothing, right? So for example, right here, the red one is positive, the blue one is negative, and so if you add them together, assuming that they're roughly equal in size, you get nothing. This is one of the main properties of waves. Waves can interfere with one another. It's possible to have two individual waves, like two beams of light, overlap directly on top of each other and have the thing be completely dark. They can literally cancel each other out. They can also add together to give you larger waves, but what's important here is that they literally add. Now, if you're wondering why I said this is different when dealing with particles, is because particles don't do this. If I have one particle, and I were treating it as a purely classical particle, and I have a second particle, number one, it's not really possible for me to take these two particles and have them directly overlap with one another. They'll bounce off at one another, and they won't add, right? So this thing won't happen. If you put them near each other, well, you just have two things there. They never actually get to overlap. Waves will, and because they are vector quantities, they cancel each other out if you put them in the same box and have them be added together in one point in time. So typically speaking, classical particles, they don't overlap with each other, they don't cancel each other out. Now, there is an argument apart from this. If you've ever heard of a scientific discipline known as quantum mechanics, one of the main postulates of quantum mechanics is particles, like atoms and molecules, can behave like waves. So under the rules of quantum mechanics, it's possible for your two particles to overlap with one another and cancel each other out. And you see this actually in a number of devices. Have you ever been for a PET scan, a positron emission tomography scan? How that scan works is basically you put in a radioactive source that creates positrons. These positrons travel through the body, get overlapped with electrons, and basically they cancel each other out. And this leads to a large release of energy. Because even though the waves can interfere with each other and give you nothing, energy still is conserved in these types of systems. So typically speaking, if you're dealing with electromagnetism, you get something like radiation being produced. But it seems weird, and it's one of the main reasons why quantum mechanics seems so strange if you ever go on to study it. But the idea is this wave-like behavior means you can literally treat these things purely mathematically, have them add up and cancel one another. Now, in terms of dealing with this, there are a couple ways to look at this. What you'll notice between this red path and this blue path, if we take two spots that are roughly the same, like this one and this one, you'll notice that they are shifted slightly. In terms of the wave equation, this has to deal with one of the parameters we haven't talked much about, and that is the phase that is present in all those sine functions that you've seen in the previous section. The phase simply tells you where a particular point is relative to a reference point. So between these two x's, which describe the two peaks of adjacent nodes here, there's an actual phase shift. And if this phase shift is an integer multiple of the wavelength, the waves line up. If this phase shift, is a odd multiple of pi, these waves will demonstrate destructive interference. Now, dealing with phases is not super pleasant. So what we instead deal with in most instances, like when you're building a spectrometer, is a path length difference. Because if your two waves are generated by the same spot, They'll start off in phase, and if they travel slightly different distances, they will reach a different point of oscillation when they're eventually recombined together. So if you're going through the section in this, or through the material in this particular section, although this is introduced in terms of phase differences, being either an even integer or an odd integer, it is far more easier to use a path length difference. For a path length difference, constructive interference occurs when you have a full integer multiple of the wavelength, and destructive interference occurs when you have a half integer multiple of the wavelength. And it's by far the more useful way of looking at things. So something's going to hold true here. We didn't really look too much about phases in the previous section. We're still not going to do so here. What we're going to look at is the difference in how far waves have traveled.